Think about something you do every day, like finding a contact on your phone. Say, Mom, you type MOM.
And boom, it's right there.
Exactly.
Yeah.
Instantly. Or like finding a word in a dictionary, or maybe a book in a huge library. How can computers find one thing so fast, whether it's searching through, I don't know, 10 things or 10 million?
Right. The speed seems
Yeah.
constant. Doesn't seem to matter how much stuff there is.
It feels a bit like magic.
It really does. But what's super interesting is that the speed, it's not just convenient, it's actually foundational. It's reshaped our whole digital world.
How so?
Well, these unsung heroes, let's call them, are working behind the scenes
Yeah.
in databases, web browsers, your phone apps, making everything feel lightning fast.
Ah, okay.
And because of that, we've come to expect information instantly. It's changed our baseline assumption about how things should work.
So it's not just faster, it actually changes what's, well, possible with organizing all that data.
Yeah.
That's a big deal.
Ex-
So if you've ever wondered how computers pull this off, or maybe you're a developer wanting to get a handle on one of programming's most powerful tools, well, this deep dive is for you. We're going to look under the hood.
Welcome, everyone, to the Deep Dive. We take these complex ideas and hopefully make them clear, showing you the elegant thinking behind the tech you use every day.
And today, yeah, we are diving into one of my absolute favorite data structures. It's a real powerhouse. And we're taking inspiration from a fantastic article, Taking Hash Tables Off the Shelf by Vaidehi Joshi. It's from her Basics series, which is just brilliant.
It really is, and we're going to lean heavily on her bookshelf metaphor today. It's such a great way to understand how these things, hash tables, work.
Right, how they work, why they're so incredibly efficient, and, why they're basically everywhere in computing.
Yeah, by the end of this, you'll definitely see why people call hash tables the Swiss Army knife of
Right.
data structures. They're just so versatile.
And I bet you'll start seeing them, or at least thinking about them, all over the place in your digital life.
You absolutely will.
Okay, so let's start with a problem. Anyone who's moved house will probably feel this one. Picture it. You've just moved, maybe across the country. Boxes everywhere, especially books.
Oh, yeah, the book boxes.
You're exhausted. You just want them off the floor, so you start checking them onto the shelves. No order, no system, just, making space.
Been there. And that immediate relief getting them off the floor, it quickly turns into a pain later.
Totally. A week later, you suddenly want to reread, say, The Great Gatsby. Where is it?
Uh-oh. You'd have to look everywhere. Book by book, shelf by shelf, worst case, it's the very last one you pick up.
Exactly. And that maps directly to a fundamental problem in computer science, doesn't it?
Yeah.
Finding one specific thing in a big pile of stuff.
Precisely. If the books are your data set, finding Gatsby is your search operation. And that haphazard approach, it scales terribly.
Yeah, imagine not just your books, but a massive library. Millions of books.
Yeah.
And someone asks for one specific title, if they're just randomly placed.
You'd be searching forever, literally. In programming, we call that kind of naive search ON time complexity, or linear time.
And being a number of items.
Exactly. The time it takes to find something grows directly in line with how many items you have. Check 1, check 2, check 3, potentially all the way up to n. It's like walking every single aisle in a giant supermarket.
Okay, so that's bad. What if we're a bit smarter? Like, we sort the books alphabetically first. Then we could do that thing where you open to the middle, see if you're too early or too late, and jump again.
Ah, binary search.
Right.
That's much better. That gets you down to O log n time, logarithmic time.
Which is way faster than linear for big collections, but
Yeah,
it's still not instant, is it? You're still doing multiple steps, comparing and jumping.
right. It's faster, but not the ideal. The dream solution, the holy grail, is to go directly to the item, instantly.
Like having a magical librarian who just points and says, Gatsby, shelf 3, 5th book in. No searching at all.
Exactly that.
Look.
Teleport straight to the spot.
So how do we get that magical librarian? How does your phone find Mom instantly? How does Google do it? That's the secret, isn't it? It's hash tables.
That's the secret. And that magical librarian is essentially what a hash function does. This is where it gets really elegant.
Okay, so how do they pull off this efficiency trick? Solving our messy bookshelf problem.
Right. So a hash table basically has two key parts. First, you need somewhere to store the data that's an array. Think of it as our actual bookshelf structure.
Okay, the shelves themselves. Got it.
And second, the crucial part is the hash function. This is the clever bit. It's like the system, the rule that decides exactly where each book, each piece of data is going to live on those shelves.
So it's not random placement anymore. The function dictates the location.
Precisely. The magic is this. When you add a book, the hash function calculates its exact spot on the shelf. And critically, when you need to find that book later, you use the same function, the same calculation, and it tells you exactly where to look.
No searching required, just a calculation.
A direct lookup, like knowing an address and driving straight there.
Okay, let's make this concrete with a bookshelf. Say we have 12 shelves, numbered 0 through 11, maybe.
Perfect. And let's use a really simple hash function for this example, let's say. Count the number of letters in the book's title.
Okay.
Then divide that number by 12, because we have 12 shelves, and the shelf number is the remainder of that division. We call that the modulo operation.
Right, the remainder. Got it. So back to The Great Gatsby. How many letters is that? T-H-E-G-R-E-A-T,
Right.
G-A-T-S-B-Y, 14 letters.
14 letters, exactly. So our function says calculate 14 modulo 12.
Okay, 14 divided by 12 is 1, with a remainder of 2.
Bingo. So The Great Gatsby goes on shelf number 2, period.
And when I want to find it later?
Same calculation. Title is The Great Gatsby, 14 letters, 14 modulo 12 is 2. Go straight to shelf 2. There's your book. Instant access.
Okay, let's try another. Pride and Prejudice, P-R-I-D-E-A-N-D, P-R-E-J-U-D-I-C-E. 17 letters.
17 modulo 12.
17 divided by 12 is 1, remainder 5, so shelf 5.
Shelf 5 it is. See? One calculation tells you exactly where it goes and exactly where to find it later.
That is genuinely cool. And that's speed. That's the O1 thing, constant time.
That is the power of O1, constant time complexity. Notice how the time it took us to figure out the shelf for Gatsby or Pride and Prejudice. It didn't depend on whether we had 10 books or 1,000,000 books already on the shelves, right?
Right. It was just one calculation based on the title itself.
Yeah.
The size of the collection didn't matter at all.
That's constant time. The lookup time is independent of the dataset size in. And that, for inserting, deleting, and especially finding data, is the absolute holy grail in computer science efficiency.
Wow. Okay. You can see why that's so important for, well, everything. Databases, websites.
Absolutely. That O1 lookup is what makes it possible for services to scale to billions of users. Think about your social media feed or streaming service. Without this kind of speed, they just couldn't handle the load. It's revolutionary.
Okay, but hang on. It sounds almost too perfect. What if another book also calculates to shelf 2 or shelf 5? Let's try The Old Man and the Sea. T-H-E-O-L-D-M-A-N-A-N-D-T-H-E-S-E-A. 18 letters.
18 letters, yeah, so 18 modulo 12.
That's remainder 6. So it goes on shelf 6. But what if shelf 6 already has a book on it? What happens then?
Uh-huh. You've hit on the key challenge. That situation is called a collision.
A collision. Okay, that sounds like a problem.
Well, yes and no. It's actually not considered a bug. It's more like an expected feature, something you have to plan for in any real-world hash table.
Really? Why is it expected?
Think about it. We have 12 shelves, right? But we could have hundreds, even thousands of books. It's simple logic, sometimes called the pigeonhole principle.
Pigeonhole principle?
Yeah, if you have more pigeons than pigeonholes, at least one hole must contain more than one pigeon. Same idea here. If you have more books than shelves, at least one shelf must end up needing to hold more than one book according to your hash function. Collisions are inevitable unless your table is infinitely large.
Which is not practical.
Not remotely practical. So, collisions will happen. The question isn't if, but how you deal with them gracefully.
Okay, so how do we deal with this traffic jam on shelf 6? The Old Man and the Sea arrives, but there's already a book there.
Right. There are several clever ways, but let's start with the most intuitive one. It's called linear probing.
Linear probing, okay.
It's pretty simple, actually. The hash function says shelf 6. We check shelf 6, and oops, it's full. So with linear probing, we just check the next shelf, shelf 7.
Just look next door.
Yep. If shelf 7 is also full, we check shelf 8, and so on. Linearly, one after the other, until we find the first empty shelf, and that's where The Old Man and the Sea goes.
Okay, that makes sense.
Yeah.
Simple enough. But how do you find it later?
Same process. You calculate 18 modulo 12, which gives you 6. You check shelf 6. Is it The Old Man and the Sea? Let's say, no, it's some other book. Because you use linear probing, you then check shelf 7. Is that it? Maybe yes. If not, you check shelf 8 and so on until you either find your book or you hit an empty shelf, which means the book isn't there.
I see. But Doesn't that potentially slow things down again? If you have a bunch of collisions all hashing near shelf 6, you might end up having to check shelves 6, 7, 8, 9.
Exactly. That's the downside of basic linear probing. You can get what's called clustering.
Clustering, like a traffic jam on the bookshelf?
Perfect analogy. If shelves 5, 6, 7, 8, 9 all get filled up because lots of books hash to that area, then finding any book that belongs in that cluster or adding a new one starts to take more steps. It's not quite O1 anymore in those clustered spots.
So linear probing is simple, but it can degrade performance if things bunch up.
Precisely, which leads to other, often smarter, collision resolution strategies. We don't need to go super deep, but just to give you a flavor.
Yeah, what else is there?
Well, one common one is called separate chaining. Instead of each shelf holding just one book, imagine each shelf holds a little list or a mini bookshelf.
Ah, so if multiple books hash to shelf 6, they just all go into the list on shelf 6.
Exactly. Shelf 6 might hold a linked list containing The Old Man and the Sea and maybe 2 other books that also hash to 6. When you look up, you go to shelf 6, then you just quickly scan that short list.
Okay, that avoids the linear walk down the main shelves.
Right. Other methods get fancier with the probing idea, like quadratic probing, where instead of checking shelf +1, +2, +3, you check +1, +4, +9, you jump further each time to break up clusters.
So you leap further away if the next spot is taken.
Yep. Or double hashing, where you actually use a second different hash function to calculate how big of a jump to make when you find a collision.
Wow, okay, so there are definitely more advanced ways to handle it.
There are, but the crucial takeaway, no matter which strategy you use, is this. Even with collisions, hash tables are designed to be incredibly efficient on average.
On average,
Because a lot depends on having a good hash function in the first place. A good function spreads the keys out as evenly as possible across all the shelves, or buckets, as they're often called.
so fewer collisions happen to begin with, and those that do are less likely to cluster badly.
Exactly. Designing good hash functions is a bit of an art and science itself, aiming for that nice, even distribution. When you have that, collisions are manageable, and lookups stay very, very close to that O1 ideal in practice.
Okay, that makes sense. The function quality is key.
Absolutely. So now we know how they work, roughly. Let's talk about where we actually find these things. Spoiler, it's basically everywhere.
Right, you said we use them dozens of times a day without thinking, like my phone contacts example.
Perfect example. Your phone isn't scanning AZ when you type mom. It hashes mom, the name is the key, and that calculation points directly to where mom's contact info is stored. Instant lookup.
Same for, like, social media, finding a friend's profile.
Yep. Usernames, user IDs. They're often keys in a hash table pointing to the user's data. Think about database lookups, too. Finding customer record, hashtag 12345 out of millions. Probably a hash table using the ID as the key.
What about on the web? You mentioned browsers.
Oh yeah, heavily used. Caching web pages, storing copies locally so they load faster next time. Hash tables often manage that cache, using the page URL as the key. Storing website cookies. Managing the structure of the web page itself, the DOM. Hash tables are involved there too, helping things run smoothly and quickly.
Spell checkers. How do they know instantly if I misspelled a word?
Again, likely hash tables, they hash the word you typed. If that hash doesn't exist as a key in their dictionary hash table, bam, it's probably misspelled way faster than searching a huge list of words.
Now, you mentioned programming languages themselves use them internally.
Oh, absolutely fundamental. If you've ever used a Python dictionary or a JavaScript object literal or a Java hash map, congratulations, you've been using hash tables directly. They are the go-to structure for that kind of key value mapping.
It's funny, you could almost argue the old Dewey Decimal System in libraries is a kind of real-world, non-digital hash table.
Right? That's a great analogy. It's a system designed to map a book's subject or author, the key, to a specific location, the shelf number, avoiding having to search the entire library. It's the same core principle.
So these things are so widespread, they've actually shaped what we expect from technology, that instant access.
Totally. We now just assume we can find any piece of digital information instantly. Hash tables are a huge reason why that expectation is often met. They make that seamless experience possible.
What about e-commerce? Searching for products, my shopping cart.
All prime candidates. Product IDs mapping to product details, your user ID mapping to your shopping cart contents, looking up your account info. Hash tables are likely working behind the scenes for speed and efficiency. Even tracking inventory levels might use them.
It's kind of amazing how much relies on this one core idea.
It really is. And the beauty is that most of the time it's completely invisible. It just works. You type, you click, you get what you need instantly. It's this effortless illusion powered by clever data structures like hash tables.
Okay, so pulling this together,
Right.
what are the big practical takeaways, whether you're coding this stuff or just using it every day?
Right. For developers, the first thing is just use them. Modern languages have excellent built-in hash table implementations, Python DICs, JS objects, Java hash maps, and so on. Don't reinvent the wheel if you need fast key-value lookups. Use the tools.
Leverage the built-ins. Makes sense.
Second, think about your keys. The performance really hinges on that hash function spreading things out. So choosing good keys that are likely to hash well, avoiding things that might cause lots of collisions is important.
So the choice of what you use as the key matters.
It does, and understand the trade-off. Hash tables generally use a bit more memory than, say, a simple list or array, because you need that extra space for the table structure itself, potentially leaving some slots empty. But you trade that memory for significantly faster access time, that O1 magic.
Speed versus space. A classic trade-off.
Classic trade-off. And finally, for devs, think about caching. If you have data you need to access repeatedly and quickly, storing it in a hash table as a cache is often a perfect use case.
Gotcha. Okay, what about for the rest of us, the non-programmers?
Well, first, maybe just a little appreciation for the engineering. The next time your phone finds that contact instantly, or your spell checker flags a typo.
Take a sec to think about the hash table likely doing the work.
Exactly. And it helps you understand why some things are instant, like looking up a saved password in your password manager, probably a hash table lookup. While other things, maybe like generating a really complex secure password, take a noticeable amount of time because they involve heavy computation, not just simple lookup.
It gives you a bit of feel for what's happening under the hood.
Right, and the core principles organizing things systematically for direct access and efficient retrieval, that's a useful concept way beyond computers. Think about organizing your filing cabinet, or setting up inventory in a warehouse, or even tagging your digital photos so you can find them easily.
Systematic placement, direct access.
Hmm.
Yeah, I can see that applying elsewhere.
It really boils down to solving that fundamental problem. How do you find stuff quickly when you have lots of it? Hash tables are just a particularly brilliant computational solution to a very general challenge. It shows the power of good abstraction and smart algorithms.
That's a great way to put it. I really hope this deep dive has sparked some curiosity for people about how this everyday tech actually functions. What was the biggest aha moment for you revisiting this?
For me, it's always realizing just how much relies on this relatively simple core concept. Its ubiquity is staggering when you stop to think about it. How about you?
I think just reinforcing how elegant the collision handling can be. It's not just brute force. There's cleverness in making it work despite the imperfections.
Absolutely. So here's a little challenge for everyone listening this week. Actively try to notice hash tables in action, or at least situations where they could be used.
Yeah. Every time you look up a contact, search for a file on your computer, use a dictionary app, even use autocomplete. Pause and think. Is there a hash table making this instant?
See what you find. And if you really want to go deeper into this and other fundamental computer science ideas, seriously, check out Vaidhi Joshi's BASEX series online. It's fantastic.
We'll link to it. It's a great resource.
So the final thought to leave you with is this. Behind almost every seamless, instant digital experience you have, there's some elegant computer science doing its job perfectly.
And hash tables are just a prime example of how these brilliant, sometimes simple ideas make things that seem impossible feel completely effortless.
Changing the world, one fast lookup at a time.